Okay, can you hear my voice?
Yes.
Okay, thank you. Okay, so let's continue on our lessons from yesterday. Let me share the slide. Okay, let's do some recap on whatever we learned yesterday. So, okay, for yesterday we already discussed about the new chapter, which is energy. Okay, this chapter is called energy. Okay, so this is the units of in chapter energy, which is we gonna learn about work, kinetic energy, and the work energy theorem. So far, we just oversee the work. We just only cover until work. Okay, we didn't yet reach to the 5.2, which is today we gonna finish the topics. Okay, 5.2, 5.3, 5.4. Okay, then we go to power, and then lastly the work done by a varying force. Okay, so this is the work done by a constant force. We are saying that W is equivalent to F dot D. W is equivalent to F dot D, where F is a force and D is the distance or displacement. Okay, in this case, we are saying that D can be either distance or displacement. But for us to understand that work, it is actually a scalar quantity, so we can define F as a vector and D is the displacement because displacement is a vector quantity. Okay, displacement is a vector quantity. Despite of the distance is just a scalar quantity. So when we multiply vectors, okay, when we multiply vectors through a dot product, okay, we can get work as a scalar quantity. Okay, so the unit for work is from here we have W equals to F dot D, which means we have F is Newton and M is meter. Newton meter, or another form is joule. Okay, the SI unit for work is joule. Okay, the same goes to energy. Okay, work and energy is related to each other. Right. So we are saying that when we apply some force, okay, to the object that have mass. So when we apply some force to the object that have mass, and that object will move at a certain distance or displacement. Now we are saying that that object will must have a work done. Okay, so that work should be work done from the man to the box, for example. Okay, and this is the work. Okay, and the equivalent work. Okay, for example, we have a lot of activity here, and to then we with a certain equivalent amount of work. Okay, every situations, every work. Okay, every values, uh, typical values of work, eh, such as the list of the activities here, okay, contain an equivalent work. That equivalent that will give you a joule. Okay, for example, we have a heartbeat. Okay, we have breaking a bond in DNA, for example. Okay, we give you some values, and this is the examples of what we're gonna cover for the work. Okay, and then again we may have situation, or if the force is at an angle. Okay, normally when we discuss force, the force is always the same axis as the displacement. Okay, when you discuss about work, or when you dealing with work, yeah, I know because I'm also teaching tuitions at the secondary level. Okay, I know that every possible situations, the force is always parallel to the displacement. Okay, force is always parallel to the displacement, whereas, okay, in this level of asasi, okay, we will cover, okay, the force at a certain angle. Okay, not just we learn here not just a force that parallel to the displacement, but we also what happens to the force when it have a component. It's just a component, because this is the true meaning of work. Work is based on F cos theta times D. Okay, I will write it back. W equivalent to F cos theta dot D. How can we get F cos theta dot D? So F cos theta is based on, okay, it's based on this kind of situations. Okay, let's say you are pulling a bag, you're pulling a bag with a certain force here, for example, with a certain force. Okay, that force, okay, and now have a situation where the force is actually at some angle, okay, between the force and also the displacement. We are saying here this is some angle. When the force have some angles to the displacement and it's not a parallel, a solid parallel line to the displacement, therefore we need to establish, we need to resolve it into its component. Okay, for example, we are using the value of here. Okay, we're gonna have F cos theta based on what? Based on our agreement in terms of how to resolve the vector into its component. Now we have F cos theta because this is the angle between vector and also a component. And when there is no vector, when there is no angle between the force between vector and the component, then become sine. Now we have F sine theta at y axis and F cos theta at x axis. Okay, so this is where we get F cos theta and also the displacement. F cos theta and the displacement. Okay, F cos theta times displacement. That means quantity of force, the component of force that parallel to the displacement. That's how we get F cos theta times D. Okay, so in the end, okay, we're gonna define that work is equivalent to F d cos theta normally. Okay, so the theta means the angle between the force and also a component. So a vector between the force and also the displacement. Okay, so the unit still joule. Okay, this is also some examples that we obtained yesterday. Okay, and this is how you gonna separate between which angle can give you a zero work, okay, which angle can give you positive work, and which angle can give you negative work. So that's how you will you will determine which work is will get you positive, negative, or zero. And definitely when the theta is equivalent to 90, remember cos 90 is 0, where cos 0 is 1. Okay, cos 90 0, cos 0 is 1. So therefore we need to know the concepts of how to get a zero work or positive and negative work. Okay, if there is more than one force acting on object, for example the situations of here, okay, we will see here a lot of force involved in these situations. For example, okay, we have a normal force, we have a gravitational force, and here we have a frictional force. There are three possible force, which is we have gravitational force. Okay, we also have a normal force. Okay, normally I just put it as N. Okay, yes. Okay, and also we also have a frictional force. Okay, in here we have air friction. Okay, now there are three forces. Okay, normally when we have three forces, so we need to calculate what is the W for air friction, what is the W for normal force, and what is the W of the gravitational force. So we need to add, and the total work is W G plus WN plus WL. So we need to know the concepts of submission of work total. Okay, submission means hasil tambah. Okay, submission adalah hasil tambah or the work total. So therefore, we need to establish what is our total force from the situations and okay. So with that things, we are discussing about this example here about how to get a work by considering every forces involved in this part of the examples. Okay, so that's how we're gonna get this kind of situations. Okay, so again, okay, I just go through. Okay, now we have two examples, example 7.3 and also example 7.4. Okay, there are two examples involved in this kind of situation, the same situation but a different approach. Okay, different approach. All right, so in here we have a normal air and also gravitational force. So we do it separately. Okay, look at how we do it separately by using a normal force and the displacement. The theta is 90. If the theta 90, then cos 90 will be 0. So that's why this work will be 0. Okay, and how about air friction and also gravitational force? Yes. Okay, the gravitational force, for example, is always straight downwards. It's always straight downwards. Okay, so now we're gonna do some resolving. We need to resolve it to its component because there is some angle involved. Okay, so this is mg cos phi and this is mg sine phi. Okay, they are using phi instead of theta. Different. It's just a symbol. Okay, it's just a symbol. It doesn't mean anything because this is phi. All right, and the theta is from our terms. It's just a theta inside the W equals to F cos theta times D. Okay, F cos theta times D. Okay, so the phi is just an angle because of due to the situation where this is an inclined situations. Okay, so the mg cos phi will definitely give 0 work. Why? Because the theta, not the phi, the theta is 90 degrees from the displacement. Can you see this is 90 degrees? Okay, this is 90 degrees. Okay, so the one that we should consider is just mg sine phi. Mg sine phi, okay, times with d, then we'll give you some work. Okay, and of course, in here we have air friction that is always opposing the motion. The car is going down the hill. Okay, it's going down the hill. So therefore, the friction should always oppose the motions of the car. So that's therefore we will get at the theta at about 180 degree. What happened that when theta is in the third or second quadrant, the theta will be -1. The theta will be negative value. Okay, and when the theta is 180, so we can see that theta 0 cos 0 will give you 1. And cos 180 is -1. It's just we put some negative to that value. Okay, and then we add up everything to get W totals here. So you can see here Wn is 0. Wa is negative F air D. Okay, why negative F air D? Negative F air is based on -1 times F air, okay, or air frictions times with the displacement. And then of course the W gravitational force is mg sine phi times D. So they put it together, mgd sine phi. Okay, so now we will get the total is equivalent to mg sine phi minus f a d. Mgd, or we can factorize it d. We put it d at the front. Okay, so right now we look at the second examples. Okay, so when we actually uh, go through again and again about how we're gonna solve the problem involving force, okay, or involving work. So we need to establish, we need to know that what is the functional force that we should consider. Okay, when you are dealing with a situation where the car is going down the hill, that means the car is moving in x-axis. Okay, remember when we do inclined situation, the axis should be like this, x and y. So when I call it x-axis, that means it should be down the hill. Okay, and when it goes up, that means y. All right. So because of that, okay, when the car is moving down the hill, that means it moves in x-axis. When we move in x-axis, we should always consider the forces that acting only in x-axis. Despite of, instead of we calculating force that is in the y-axis. Okay, we know that everything in y-axis I should put in blue color, or yes, as green color. This is y, and also mg cos phi is in y-axis. Definitely, that both situation will give you zero work. So the one that functional more is the one that from air friction, okay, air friction, and also mg sine phi. So we just concentrate on what is the total work done of fx, which means at that point we will get, okay, if the car is going down that way, so we put it at the front, mg sine phi minus is air frictions. So this one should be the negative fx. So w is equivalent to the total work done will be equivalent to summation of fx times d. So we put it as mg sine phi minus air, okay, times with d. With that things now, okay, we will get the same value as the one that we did on the previous examples. So it's just saying that, okay, this kind of examples, this kinds of situation, that means we need to know, okay, what is the submission of f that involved in the motions, which means in this case the motion is in x-axis, and therefore we only consider the forces that acting on the x-axis alone, okay, instead of we considering everything, okay. But it's up to you. You can do both. You can choose whichever you want to use if the problems occur. So you can choose either to calculate it separately, or you just focus on which is the correct force that times with the displacement. Okay. So this is some examples, other examples of using the component of force that parallel to the displacement. Remember, we need to know the parallel of force that component of force, component of force that parallel to the displacement. Okay, and what happened when we also involve friction? Yes, okay. The situation is when we have, okay, a certain problems, okay, that involve coefficients. If you look carefully inside the question, it's also stated here coefficients of kinetic friction. That means when this occur, we know this is Fk, which means the coefficients of kinetic friction. Okay, and then of course, when we considering coefficients of kinetic friction, that means it always oppose the motions, especially in kinetic, when the object is moving. Okay, so everything must be considered using friction. All right. So I think that will be what we learned yesterday. Okay. Okay. So right now we will continue our lessons using a kinetic energy and the work energy theorem. So what is kinetic energy and the work energy theorem? Okay. Now it happens that when positive work is done on the object, okay, the speed will increase, but at the same time, the negative work, when whatever happens when negative work is done, the speed will decrease. So the work will depends. It's either positive or negative. Will depends on the situation of the speed. That means work and speed, okay, is related to each other. Okay, it's saying here when the work done is positive, that means the speed increase. And when the work done is negative, that means the speed is decreasing. Okay, so it's good to know that. And of course, this happen when we have some algebraic to manipulate the equations of motion. For example, what happens when you deal with the total work? Okay, so it is saying that, okay, the theorem, okay, is right now involving W and also speed. Okay, W work and also speed. So how can we relate between W and speed? Okay, so after algebraic manipulations of equations of motions, okay, we will actually get, okay, the total work done is equivalent to, okay, the the difference between half, which is the kinetic, the maximum kinetic energy, or the, which means half mv final square, minus with the half mv initial square. Okay, what is this equation? This equation is the kinetic energy. Okay, this is also a kinetic energy, because the kinetic energy, okay, we will define the kinetic energy as Ke equivalent to half mv squared. That means half m is mass, v is velocity, or v is the speed. To be on the precise, is v is speed. Okay, half mv squared. And the energy theorem, okay, so when we call that as a work energy theorem, remember, okay, before this, work is related to W equals to F D cos theta. So that means work is related to force. Okay, and what happened when we don't have force but we have been given to the with the speed? Yes, we can also find the total work, because the total work W total is equivalent to a delta of KE. What is delta KE? Which means the, the difference between kinetic energy final and also kinetic energy initial. Half mv square minus with half mv initial square. Okay, so this is the work energy theorem. Okay, relating work and also energy. So what kind of energy? This is kinetic energy. So remember, please remember, this is kinetic energy. This is at the moment, okay, it's just about work and also speed. That means work positive, speed increase. When work negative, speed will decrease. All right. So let's look at the situations. Okay, a 4.1 kilogram box of books is lifted vertically from rest at a distance of 1.6 meters. Okay, but if you look carefully, this is the situation is you lifting the box. Okay, the man is lifting the box. That means the motion is in y-axis with a constant upward and applied force. Okay, so that means this is F. Very constant force. That means acceleration is also a constant. Okay, find A, the work done by the applied force. Find A, the work done on the applied force. Okay, so I think when you have Y, you have F. Okay, so you can use W equals to FD. Okay, just look at another one. Is the work done by gravity, and see the final speed of the box. Okay, the work done by the gravity and also the final speeds of the box. So let's look at what we should do. Okay, right now we have applied force, applied work, which means we have a box that's going lifting at 1.6 meters. Okay, and this box is 552 by our calculations. The upward applied force is 52.7 Newton. Therefore, okay, so remember we have W equals to FD cos theta. Okay, FD, so this is F is 52.7, D is the distance, which is 1.6, and cos theta, here theta is 0. Theta 0 equivalent to 1. Okay, so therefore we can get 84.3. Please take out your calculator and calculate with me. Right? And right now, okay, because that is the work done by the applied force. So we need to know. So from here, we measure this is the applied force, which means we apply some force to the box, while at the same time, there will be some another type of force that is going down, which is, we call that as the gravitational force. This is a applied force. If the box is not lifting, is the box on the floor, so that means it's only occur, it's only have a normal force. But right now, we try to lift the box, okay, away from the floor, which means we will have an applied force and also a gravitational force. Alright, so the gravitational force is going down, and because of that, okay, we're gonna calculate the part B, which is the work done by the gravity. Okay, before this, the work done by the applied force. So we need to know this is also the work done, and this is also WG. This is WF. Okay, the work done by the applied force, and WG is the work done by the gravity. So in this case, we can measure is using WG equals to mg cos 180. Why cos 180? Because theta is 180. Due to what? Because the displacement is going up, okay, going to the positive y, and the mg is going to the negative y axis. Therefore, the theta is 180. Cos 180 is equivalent to negative 1 here. Okay, times with 1.6, and of course we will get a negative value of work. Okay, look at how they calculate, look at how they represent. Okay, but right now slightly different from the G, because M is 4.1 kilogram while G is 9.8 meter per second square. And of course you will get some different value here. Okay, please calculate. Okay, we will get the value. And of course, when we do some total work here, which is the total work done, by considering what is the applied work, a force for work for force, and also work for the gravitational force, right? So we're gonna add W, both 84.3 and also 64.4. So you will get 19.9 joule. Okay, so that is that work in total. So therefore, from this work, this is work total. Okay, we can use a delta KE, which means use the work energy theorem to find what is the final velocity. Obviously, the initial velocity is 0. Okay, because the box is lifting from rest, so V naught is considered to be 0, while VF, we want to find VF. So when we calculating properly, we will get the value at least 3.12 meter per second. So you can see from this example alone, okay, we may have two kind of situation and two kind of problems that can be solved using two equations. Okay, from what we learned, especially using work that is equivalent to force, and another one is work that equivalent to energy. Okay, because work can be defined with two things, which is we have Fd cos theta and W equals to delta Ke. Okay, this is pulling a slab. Okay, a boy exerts a force of 11 Newton. Okay, this is force. 29 degree above the horizontal on a 6.4 kilogram slab. Find the work done by the boy. Okay, the work done by the boy and the final speed of the sled after it moved 2 meters. Assuming the sled starts from rest. Oh no, we have an initial speed, which means we have V naught equals to 0.5 meter per second. And slides horizontally without friction. That means there is no friction involved. Okay, so for first and foremost, we need to do work done by the boy. So in order to do that, we need to know what is the work first. Okay, the work done. So we need to know which is the component of force that involved to that work. Okay, which means right now we have 11 Newton at the 29 degree. So in here we should calculate 11 cos 29. Okay, so in this case, here you will get the component of F times with the displacement time with 2. Now you will get 19.2 joule, which means this is the total work done. Okay, but remember, okay, the second part is the final speed of the slab after it moved 2 meters. Okay, after it moved 2 meters. Okay, so right now, from the work energy theorem, okay, we're gonna write it as W equals to delta KE. Okay, W equals to delta KE, and this is MV final square half MV initial square. Okay, is equivalent to total work. So right now, 19.2 is equivalent to that value. So this one will become this one is not 0 because V initial is 0.5. So you need to add everything in order to get VF. Okay, and do some algebraic equation, simplify algebraic equations in order to get 2.5 meter per second. Okay, 2.5 meter per second. Okay, so that's how you done, how you did the problems that involve force and also work done in terms of force and work done in terms of energy. Okay, now we look at the work done by a conservative force. Okay, what is the work done by a conservative force? Okay, if we try to look at the situation first, if we pick up a ball and put it on the shelf, we have done work on the ball. Okay, we have done work on the ball. That means we do work to that ball. Okay, if we can get that energy back, if the ball falls back off the shelf, in the meantime, we say the energy is stored as a potential energy. So in this case, we are saying that we do some work to that ball. Okay, you're saying we do some work to that ball and we can get that energy back. If let's say all the forces, all the possible work from the one that we did, which is the ball, right now return or fall back from the shaft and do it to us. Okay, come back to us. So the energy will store as a potential energy. Okay, let's say, okay, try to imagine that we put a ball on the shaft, okay, slightly higher than you, okay, and that ball obviously have a potential energy. Okay, this is how you want to work done by a conservative force. That means you want to do the work, and at the same time, that work related to the potential energy. Okay, so right now the work done against frictions, however, is not stored as potential energy. Okay, remember one thing, when it involves friction, okay, it doesn't involve a potential energy. Instead, it is dissipated into forms of energy such as heat or sound. Okay, and the definitions of potential energy is the work done. Okay, this is in the work done by a conservative force is equal to the negative of the negative of the potential energy. So what is the equal potential energy? WC is equivalent to negative delta U. WC is equivalent to negative delta U. Okay. 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 This is, for example, a gravitational potential energy getting from the one that the swimmers want to do some somersault diving into the swimming pool, which has some height from the level of 0. Okay, so this is called mg. So this boy, okay, if you look carefully, the potential energy comes with the mg times y. Okay, mg dot y. So mg is force and d is the displacement. F and d is displacement. Therefore, this is the kind of work. And this kind of work we want to consider as to be potential energy. So it have its own name, which we call it as potential energy. So the potential energy happens, or potential energy will give a different value at a certain level. For example, because the potential energy needs to have some height or some y in the case. So we are saying that at this point the work will be zero. So in this case potential energy zero. What happens when you have at the y? Okay, when we have a certain height, then the work will becomes mgy. That is also because of potential energy equals to mgy. Okay, so this is one thing that you need to know. The potential energy equivalent to mgy. Okay, an 80 kilogram. Okay, look at the examples. 80 kilogram mountain climber is in the final stage of the ascent, which uh, is based on 4,301 meter high Pikes Peak. Okay, so this is called a mountain. Okay, a mountain that contains 4,300 301 meters high. Okay, so what is the change in? Let's look at how they write the questions. What is the change in gravitational potential energy? Okay, gravitational potential energy. Look at how they write down. Okay, this is not a gravitational force. This is gravitational potential energy, because when we talk about potential energy, it must involve with the situation where it must have some a distance in y-axis, for example, because distance in y-axis is always because what we have already established that work, a conservative work will be done when we have a potential energy. Okay, for example, the one that we put the ball on the shaft. So the shaft is as I have a certain height. That certain height will give you certain value of work, and that is what we call potential energy. Okay, look at how the example says. So what is the change in gravitational potential energy as the climber gains the last 100 meters of altitude? The last 100 meters. So that means, if you look carefully, this is how they write it here. So this is level 0 at the sea level, sea level 0, and the top of the mountain is 4,300 meters. So this is 4,300 meters, and the climber is 100 meters to the top. Okay, 100 meters to the top. So right now we are saying that this climber is at the level from the sea level at 4,201 meters. Okay, 4,201. Okay, let u, look at the example, the question, let u equals to 0 be, okay, there are two situations. Number one, let u equals to 0, that means potential 0 at sea level. Number A is at sea level, that means here, and also at the top of the peak. Okay, either is at the sea level or at the top of the peak. So we need to consider two situations. Okay, situations in how actually these problems will train you, will guide you. Okay, our point of view, or the value of you need to know the correct value of y based on our reference point. Okay, based on our reference point. If there is a situation where you take potential energy 0 at the sea level, so what happened at the top of the mountain? So here Okay, we can say that the potential energy is based on the change in potential energy based on mgy final minus mgy initial. Okay, so what is mg? Right now, the different things is just we can mg, because it's just the same, y final minus y initial. Okay, so right now, let u equals to 0 at sea level. So this should be your y initial and this should be your y final. So y final is 4301 and y initial is 0. So you may put this as 4301. Okay. So maybe you can take from the climber's point of view. So 4301 and 4201. So we will take y final here at first place. And of course, this is y initial here based on the sea level. Maknanya potential energy 0 dekat sea level. So we, after some calculations, we will get 80,400 joule. Okay, 80,400 joule at the when you have potential energy 0 at sea level. So that means potential energy at higher level 4201 until 4301 will equivalent to 80,400 joule. Okay, so let's look at what happened when you have potential energy 0 at top of the mountain, mountain. Okay, so that means here right now potential energy 0 at this point. Yes. Okay. So what happened to us is our point of view have been different now. So we need to take the initial, the final point, which means the final is based on mgy also. Delta PE is equivalent to mgy final minus mgy initial. So final right now is 0. And the initial one is negative 100. How we get it? So if we take this one as 0, so another 100 that is 100 meters below the 0 point is called negative 100. And before this, at part A, we calculate it based on 4301 and 4201. So they are different. This is final, this is initial. So that's why when we take that value, don't forget to put negative at 100. So we will get the same value, which means 80,400 joule is based on our point of view, reference point. So if one students take 0 at the top of the mountain and calculate it where is the climbers going to do a certain work. So when the climbers is 100 meters to the top, so we can calculate 80,000. But if we take sea level as 0, so that means the climber is at the 4201 until 4301. So 4301 will be final, 4201 will be initial. So that is also equivalent to 80,000. So this is the proof that regardless of where we take, we need to know the difference between the difference between displacement or distance from the potential energy is very very emphasized on y. Mg times y. That y is delta y. So that's how we get delta PE. Okay. So let's look at the possible examples. This one taken from your textbook. A diver of mass m, drops from a board 10 meters above the water surface. 10 meters above the water surface. Neglect air resistance. So this is kind of assume. This is also one possible word. They can we can mention it, neglect air resistance. That means we should avoid, or we should assume that there is no air resistance. Use a conservation of mechanical energy. That word. Okay, use a conservation of mechanical energy to find his speed 5 meters above the water surface, and find his speed as he hits the water. Okay, there are two possible situations here. When the question asks you to use a conservation of mechanical energy. So what is conservation of mechanical energy? So first, okay, we need to know the concepts of energy. Okay, okay. The mechanical energy, the total mechanical energy, is based on, okay, E is based on the delta KE plus delta PE. Okay, that is total mechanical. And you know, the concepts of energy is conserved. What does it mean by energy is conserved? That means energy initial is equivalent to energy final, because when energy initial minus energy final, the answer is to be 0. So that is how we mean by energy is conserved. Okay, EI will equals to EF. Okay, and then because of that, when we have energy, and energy is delta KE plus delta KE plus delta PE. Okay, so how can we write down the equations? Okay, I put it here. Delta KE, energy is delta KE plus delta PE. So when we apply it to the conservation of energy, so right now it becomes like this. Okay, EI equals to EF. Energy initial equals energy final. So what is energy? KEI plus PEI equivalent to KEF plus PEF. Okay, so that means this is initially and this is final. Okay, so this is where we get to know the conservation of energy. Conservation of energy. Okay, so this is the correct terms of how to write the conservations of energy. The same goes to conservations of momentum. Okay, so that's why normally in your secondary school you mention u square m1 u1 plus m2 u2 equivalent to m1 v1 plus m2 v2, for example. That is due to this part, the energy conservation. Okay, all right. So when you look at the examples, okay, a diver can neglect air resistance, use conservations of mechanical energy. Because of what? Okay, the situation now will you look carefully at the equations. Ke is equivalent to half mv squared, while pe is mgy. Okay, because this is y exists, so normally we put it as y, meaning that the height, or maybe somebody will use it as mgh. The same thing happens, the same goes to this value. Okay, so ke is half mv squared, while pe is mgy, or you can write down as mgh. All right, so ke will depends on the speed of the object, and pe is depending on the height of the object. Okay, so we will see that if the diver is at the top of the board, okay, before it try to dive it at the 10 meters high, so basically at this level, okay, the kinetic at the moment, the kinetic will be 0. okay, at the what? Kinetic will be 0. And at this point, we are saying that the mgy is maximum. Okay, maximum. Have a maximum value because this is the highest point that the diver will go through. Okay, this is the highest point because when it try to dive, okay, okay, to the surface of water, or okay, we can see that the height of the diver will decreasing. Okay, will decrease from time to time until it reach the water surface. So because of that, we are saying that here the potential energy, okay, maximum at the highest point, but at that point the diver is not moving. Okay, because of that, the kinetic energy will be 0. And what happened is at the point where here, okay, this is where the kinetic energy become half kinetic energy, and the maximum energy will become half at that time. Okay, kinetic energy become half, the potential is decreasing into half value. And at this point, when they reach at the highest level, or the lowest point, this is where you got the kinetic energy maximum, where potential energy 0. Okay, kinetic energy maximum at that point, because that is the highest speed the diver can get, and the potential energy 0 at the lowest point. So because of that, we need to know to find his speed 5 meters above the water surface at point 1.5 meters over the water surface. And remember, please write energy initial equivalent to energy final. Always start with that on energy conservation. Okay, it will save you. It will give you some confidence in writing equations involving KE and PE. Okay, so we should always put it in this way. Okay, every E must come with the KE and PE, regardless of situation. Maybe at that point KE is 0, for example. Don't bother about that. Okay, don't bother much. Just focus on this is the correct term: KE initial, PE initial, KE final plus PE final. Then you move. Then you put the equations accordingly, which means KE is half MVI initial square, MV final square, MV initial square, for example. Okay, plus with MGY initial plus equivalent to half MV final square plus MGY final. And then after that, then you define where is your situation. Okay, for example, this diver you want to calculate the final the velocity at 5 meters height. Okay, at 5 meters height, the potential is still half. The potential is still the value of potential is still there, and there is some kinetic energy involved, because right now the diver must have a speed. But at the moment, initially, the diver is 0. Okay, because the diver doesn't move. And of course, at that point, that it will be mgy initial, which means the highest potential energy at that point. Okay, and then they cancel out all the m's and just left gy initial plus equivalent to half V final square plus GY final. So after some calculations, they will get 9.9 meter per second. 9.9 meter per second. Okay, so find number B. Find his speed at his as he hits the water. As he hits the water, so mgy everything potential energy initial is right now the energy from the potential energy been converted to a kinetic energy final. Every energy have been transformed from the potential energy into kinetic energy. So that's why we normally this, if you look carefully, or you always get to know this kind of equation. mgh or mgy equivalent to half mv squared. Okay, because this is the main equations that always comes in your secondary school. mgh plus half mv squared. Okay, this is how they get the mgh equals to half mv squared. It comes from the conservation of energy. But the correct way to learn about the conservation of energy is you write it in full. KEI initial plus PEI initial, okay, equivalent to KE final plus PE final. And then you write the equation. Okay, don't just simply assume that MGH equals to half mv squared, because when MGH and half mv squared is based on the situation, okay, at the associate level, you can be asked at any point of the distance. Okay, maybe at some 8 meters high, maybe at 2 meters high, maybe at 1 meters high. Okay, it's not necessary ke mgh equivalent to half mv squared. Okay, now let's look at another examples. But this one, I want to just highlight in terms of potential energy of the spring. Okay, the potential energy of the spring is given by the equations of PE spring is equivalent to half kx squared. Okay, half kx squared, which means half is a half value, k is the spring constant. Okay, k is the spring constant and x is elongations. Spring constant and x is elongation. Okay, elongation square. Right? So look at how they get the values. Okay. So when a force of 120 Newton is applied to a certain spring, it causes a stretch of 2.25 centimeters. This is delta x. Okay, remember when you deal with the spring, remember it's not just about potential energy, because potential energy of the spring is half kx squared, and you should know also about Hooke's law, which we have F equals to kx. Okay, we must always relate the half kx squared and also F equals to kx. What is the potential energy of this spring when it is compressed by 3.5 centimeters or expanded by 7 centimeters? Expanded and also compressed. Look at how they write. Okay, compress, they use compress, and they use expand. Compress maksud dia tekan ke dalam 3.5 centimeters. Expand, kita tarik 7 centimeters. Okay, so first you need to calculate the K. So using this kind of equation, Hooke's law, okay, which we get 5330 Newton per meter. And by calculating, okay, compress 3.5, so you need to establish to the right. Okay, when the spring is going to the left, that means it compressed. So the compress means, let's say this one x equals to 0. So when you look at the your left, x will be negative 0.035 meters. Okay, because x should be right in meters. Because you look at k, the value of k is Newton per meter. Okay, so that's why when you use a Hooke's law, the x should be in meters. Okay, so you calculate it and you will get 3.26 joule. Okay, accordingly, regardless of the x is negative, but considering that x will be square, so that will give you positive value. So the potential energy at 3.5 compressed is 3.26 joule, while when we have expanded to 7 centimeters, So we just calculate it using half kx squared in order to get 13.1 joule. Okay. Okay, now let's look at the other situation, slightly more complicated than the one that we did before this. Okay. Uh, a, a 50 kilogram circus acrobat drops from a height of 2 meters. Okay, drop, jatuh bukan jatuh maksudnya dia lompat drop daripada atas, drop from a height of 2 meters straight down. Maksudnya bukan sayangnya dia jatuh straight down onto a springboard with a force constant. So ini ialah nilai apa? Force constant ialah nilai K. Ini ialah nilai Y. In figure 5.22, by what maximum distance does she compress the spring? So dia nak apa ni? Delta Y. Okay. Dalam situation ni, the spring is not in x-axis but in y-axis. So before this, you know, F equals to kx. And F can be also equals to ky, depending on the situation. Maybe you can see that the spring is in y-axis. Okay, for example, this kind of spring. It's just the same things, which is the distance or elongations, but we precisely put x because that should be elongation in x-axis, and this should be the elongation in y-axis. Okay, now the situation now is we will see that this girl, the acrobat, should have, okay, at first, the mechanical energy, which means we should consider energy initial equivalent to energy final. You look carefully and how they write the equations after this. Okay, so the situation now is the acrobat move from the certain level of height. That means she must have mgh or mgy. Okay, mgy, for instance, mgy. Okay, and then at the same moment, she will move. So definitely she also will have half mv squared. But at this moment, maybe the initial part will be 0. What happened when she tried to move it here? Okay, so we can say that, okay, and then of course when it involves spring, now we should consider half kx square as its potential. So therefore you can see at the equations, at the bottom equations, okay, equations number 1, for example, E initial equals to E final, where at the E initial you will write it down as KE initial plus PE PEG means PE girl, girl initial, and PES means PE spring. That's why PEG and PES spring. Okay, and this one is equivalent to KE plus PEG plus PES final. And our job is to get to know that equations, because everything here, okay, it's not just necessarily to calculate everything. Okay, for example, okay, it starts from a potential kinetic energy 0. So KE initial will be 0, and of course it stops at it steps on the board, and the board will compress from this level to this level. So we want to know what is D, what is the displacement of the spring, or in this case we want to find what is Y. Okay, what is Y? Not Y the height, okay, not, but the different, the elongations of the springs when the girl steps on the way down to land. Okay, so that's why it starts from the mgh. Okay, it's actually mgh plus mghd. Okay, mghd due to what? Okay, the distance, okay, is also 0. mgh plus d, mgh, this is the height of the original height, and then it have some mgh over here, and mghd, okay, mgd. Okay, this is one potential and this is another potential. Okay, potential of the spring becomes mgd. Okay, Of course, so write down it as kinetic energy 0 and potential energy at the of the girl becomes 0 when it reach at this board. But this board right now, okay, at the final point will have half kx squared. In this point, they write it down as half kd squared. Okay, don't get it wrong. Okay, it can also be right as instead of half PE spring half kx squared, you can also write it as half kd squared, just to make sure that you know that is the elongation. D is just the elongations. Okay, so right now we will reduce to the point where we reduce the point where we will have a MGH of the girl strictly equivalent to half kd squared. Okay, half h plus d is equivalent to half kd squared, and then with the proper d, we will get d equivalent to 0.56 meters. Okay, 0.56 meters. Okay, so this is very good examples. Okay, it not just involve about work, but it's also involve work, but in terms of non-conservative work and also conservative work, in which we will explain it in terms of kinetic energy, potential energy of the springs. Okay, so please, before we continue, we just need to focus on conservation of mechanical energy. Then we take a break for a few minutes, for you to maybe to go to the toilet or whatever you want to do. Okay, we just take 1 or 2 minutes break. Okay, is there any questions? Okay, so let's continue on our lessons. We share the slide. Okay, so right now, this is conservation of mechanical energy, which in this case, the total energy is based on the potential energy plus KE. Okay, PE plus KE. And the energy, conservation energy is telling you that energy final is equivalent to energy initial, or you can say vice versa. Energy initial equals to E final. E initial equals to E final. Okay, so this is the situation that I explained it before this. Okay, let's take a look on how it involve the total mechanical energy. In the bottom of the ninth inning, okay, the player hits a 0.15 kilogram baseball over the outfield fence. Okay, that means he's going to hit the home run. The ball leaves the bat with a speed of 36 meter per second. Okay, this should be initial velocity. And a fan in the bleachers catches at 7.2 meters above the point. Okay, above the point where it was hit. So 7.2 meters. So this should be high or assuming frictional force can be ignored, find the kinetic energy of the ball when it is caught. Okay, and B is speed when caught. Alright, so we need to do some energy initial. Always start with this equation. Energy equation equals to E final. So half mv initial square plus mgh initial plus half mv final square plus mgh final. Okay, final and initial. So when it hits with the initial value, okay, look at this value. Okay, it's calculated here. Initial value 0. Okay, and then of course kinetic initial potential energy potential energy is 0 because y height at the from it was hit is 0. So that's why potential energy is 0. Kinetic energy is half mv initial square, which we have 97 joule. And then we have potential energy because it has been lifted from 0 until 7.2 to become 11 joule. And kinetic energy final at half mv final square. So ui plus ki equivalent to uf plus kf, and in the end we will get the kf, the kinetic energy final is equivalent to 86 joule. Okay, so that 86 joule is equivalent to half mv final squared, and then we will find what is the velocity final. So in this case we'll have 34 meter per seconds. Okay, so another part, okay, another examples. Well, we're gonna have a lot of examples in this topic because in order to understand a certain topic, a certain situation, we need to look into the real situations or for examples. Okay, a 1.7 kilogram block slides on a horizontal frictionless surface until it encounters a spring with a force constant. So this should be K. The block comes to rest. The blocks comes to rest. That means the final velocity will be 0 after it compressing the spring a distance of 4.6. This should be delta x or the elongation of x. Find the initial speed of the block. So this will cari V naught. Ignore air resistance and any energy loss when the block initially contacts the spring. So it's very, very precisely we need to know the concepts of physics whenever it comes to the assuming. Okay, that's why you can see a lot of questions in physics always have ignore air resistance, because when we considering many things, so we need to calculate it all together. But when by ignoring air resistance and all energy loss, we can say that all the total energy from the potential energy, okay, have been directed towards the kinetic energy. Or we can say that there is no heat, no energy loss during the situations. Okay, so this is potential energy initially, okay, because of no values of no height. Okay, the situation is the height is just and then the potential energy in this situation comes from the spring alone. Okay, when there is no compression, so therefore the initially the potential will be zero, and the kinetic is maximum at that time, initially half mv squared. And at the final point, okay, and it becomes half kd squared or half kx squared to the potential, and the kinetic energy maximum, kinetic energy final is equivalent to zero, because the block have been stopped by the spring, and then because of that, spring will be compressed. So at that moment, the kinetic energy, everything, every points of the kinetic energy, every value of every uh, energies from the kinetic energy have been transferred to the potential energy of the spring. So that's why we can say that U starts from the energy initial equals to energy final, but right now it just involves half mv initial square plus half kx initial square equivalent to half mv final square plus half kx final square. Okay, so in this case, this one 0, this one 0. So only left is half mv squared equals to half kx square. So you can cancel out how the half for mv squared equals to kd square. In this case, the v will become 1.09 meter per second. So a lot of examples, you can try it out. Of course, during the tutorial, you can also do the tutorials, the question inside the tutorials. Okay, so let's look at the situations of the work done by a non-conservative forces. Okay, so in the presence of the non-conservative forces, the total mechanical energy is not conserved. Okay, the total mechanical energy is not conserved. That means we cannot say that in the non-conservative force, the energy initial is not equal to the energy final. Okay, we cannot say that. We cannot say energy initial. We must say energy initial is not equal to energy final, and not just this one. Okay, because why? Okay, because we need to do some things to that non-conservative forces. Okay, because positive non-conservative work increases the total positive non-conservative work increase the total mechanical energy. Okay, while the negative non-conservative work decreases the mechanical energy, can be converted into other forms. Okay, so let's look at what the examples of the non-conservative forces. Okay, deep in the forest, a 17-gram leaf falls from a tree and drops straight to the ground. Okay, if its initial height was 5.3 meters, okay, initial height is 5.3 meters, and its speed on landing was 1.3 meters per second, how much non-conservative work was done on the leaf? Okay, so basically, I just said before this that we cannot say energy initial equals to energy final. Okay, but we need to calculate it, the non-conservative forces. So how to calculate it? We must use. That's why the problem is you can calculate the non-conservative forces by using E energy initial equals to energy final. Yes, of course we have to use that value, but we must consider one thing: the value that initially cannot be equals to final value, because it should be converted to other forms. Okay, so let's look at these examples. All right. Right now we have 17 gram leaf. Okay, daun 17 gram from tree and drop straight to the ground. Okay, so initially that leaf is a vi ataupun initial velocity 0. Okay, and that will give you final velocity because it's 1.3 meter per second. So this is vi equals to 0, v final 1.3 meter per second. Okay, so the initial height was 5.3. So this is 5.3 meters, and this speed was how much non-conservative work was done on the leaf. Okay, based on how to calculate non-conservative forces or how non-conservative work. So in order to do that, we need to establish EI equals to EF. So what is EI? What is EF? Okay, we must calculate based on our term half mv initial squared plus mgy initial equivalent to half mv final square plus with mgy final. Okay, so by calculating it, half mv squared, well, potentially uh, the kinetic energy will be 0, okay, because there is no movement. Okay, the initial velocity is 0. Now we only left with mgy initial. So mgy initial, this is mgy initial, 0.884 joule, and this is 0 for the ke initial. Okay, so the total of the ke of the total of the energy initials, it should be 0.884 joules. And now we calculate using potential. So when the leaf drop at some level, okay, so that means the mgy final will be 0. Okay, 0. And the kinetic energy final based on the last speed being given to us is 0.014 joule. So in this case, the energy final, okay, the energy final is equivalent to 0.014 joule, while energy initial is equivalent to 0.884 joules. So you can see now, okay, E final is not equivalent to E initial. So we calculate it separately. Okay, separately, because we should know that non-conservative work, E initial is not equals to E final. Okay, it's not equal to E final. So we calculate separately, okay, the total energy initial and also the total energy final, and then we minus it, because E final minus E initials. Okay, so you will get 0.014 minus 0.884, so it becomes negative 0.87 joule. So this is our non-conservative work. The value for non-conservative work is negative. We are saying that here. Okay, the negative non-conservative work decrease the mechanical energy. So when we calculate the mechanical energy, it have been decreased from initially to final. But when the total mechanical energy increase, that means we will have a positive non-conservative work. So you cannot imagine, we cannot say that it always must be a negative non-conservative work. But we should always calculate it, okay, separately between initial and mechanical energy and also final mechanical energy in order to get the situation on how to calculate the non-conservative work. Okay. All right. So this is another examples. Okay. So a 75 kilogram diver steps off a diving board and drops into a water of 3 meters below. Okay. So that means at this point, half ke initial becomes 0. Okay. At some depth, d, below a water surface, the diver comes to rest. Yeah? The diver comes to rest, and at this point, a PE initial is mgy. Okay, so initially, this is initial. This is total initial. And what happened at the final point? So at that final, we will see that it also contains mg, but depending on the situation, the boy have already dropped into the water slightly, so you will have a negative y. Okay, mg negative y, but the velocity is also zero. So ke final also zero. So by considering that, we can say that the non-conservative work, okay, you just minus because energy and work is related, okay, with the unit joule. Okay, you need to calculate E final minus E initial. The E final minus E initial, so you will get to know that mgd. Okay, where did I stop just now? Kat mana saya berhenti tadi?
Yang orang terjun kolam.
Ya, yeah?
Yang budak terjun dalam kolam.
Oh, berjaya kita. Okay. Oh, alright. So sampai sini, yang example sini dah belum lagi ya? This one.
So yang
Ini
budak
belum.
terjun kolam tu tak belum habis lagi.
Oh, tak habis lagi. Okay. Okay, tak perasan tadi. Alright. Okay. Alright. Okay. So kita tengok balik orang ni ya. So in this case, just nak make sure awak betul-betul faham that the non-conservative work is based on energy final tolak energy initial. You must calculate separately. Faham ya? Energy final siapa yang ada? Okay, mesti kena start dengan PE final plus with KE final. Satu, calculate it separately. Lepas tu, ditolakkan dengan PE initial plus KE initial. Kita calculate separately. So in this case, kalau kita tengok sebelum dia terjun, okay, V not dia 0. So dekat sini half MV ataupun saya tulis KE lah. KE 0. PE dia ialah MGH. Okay, MGH. Okay, final dia nanti, okay, sepatutnya budak ni dia terjun ke dalam air. So biasanya kita calculate semua dekat air lah. Tapi dalam kes ini, dia terjun sampai ke dasar. Okay, sampai ke dasar. So, sampai ke bawah ni. Bila sampai ke bawah ni, once again, KE dia akan jadi kosong. Dan pada masa ini, PE dia ialah mg delta H. Ada GD lah, ada D sikit. Di bawah ni maksud dia, ini ialah ketinggian D. Ketinggian D. So, ini final dia, ini initial dia. Tolakkan. Okay, tolakkan saja. Okay, sama juga dalam kes yang terbaru ni, which is kes yang ini. Ni sama juga kes dia. Okay. Maksud dia nanti kita nak calculate the non-conservative. Tapi dia tak bagi tahu. The question doesn't state directly to calculate the non-conservative work. Okay, but how do we know? So, kita kena calculate separately. Contoh dia. It's already given here. A block of mass M1 2.4, mass M2 1.8. Okay, separately I show you. When the blocks are released from rest, when the blocks are released from rest, they move through a distance D equals to 0.5. So the block maksudnya bila rest dalam keadaan sekarang dua-dua tak bergerak, and then bila M2 move, dia akan tarik M1 ke sebelah kanan. Bila M2 dah sampai bawah, maknanya M2 dah sampai sini, M2 hanya duduk di level ini saja. Tapi dia still lagi di atas ni. So in this case, well, we will see that, okay, the tension is still there, the friction is still here. So here we have M2G, yang ke atas dia tension, tapi itu ialah force dia lah kan. So right now we need to calculate it, energy initial siapa, energy final siapa. Okay, so energy initial siapa yang ada? Okay, siapa yang ada ni mesti bergantung kepada PE initial plus KE initial for both situations. Okay, so right now kena tahu dulu lah what is PE initial. PE initials here we have, untuk M1 kita ada M1 GH, ketinggian dia kan, GH daripada floor. Okay, tengok daripada floor, ketinggian dia ialah H. Okay, plus dengan M2 berapa ketinggian dia? D. M2G D. Okay, itu ialah PEI. KEI untuk M1 kosong. Okay, untuk M2 pun kosong sebab dua-dua tak bergerak mula-mula. So untuk PE, untuk E yang ini adalah M1GH plus M2G GD. Ini dia buat gantian ini just nak memudahkan kamu faham lah. And then bila dia release, okay, when it release, the M2 will go down, will touch the ground. M2 akan jatuh ke bawah. Okay, pada masa yang sama, M1 akan bergerak sedikit ke kanan, will move to the right a little bit at 0.5. Okay, at 0.5. So that means kita kena calculate pula what is the P final. So at P final, M2 dah jadi kosong sebab dia dah jatuh ke bawah. Tapi M1 still ada, dia masih lagi M1G H plus 0. KE final. So KE final ialah M1 half M1 V square, okay, plus dengan, dia dah bergerak half M2 V square, M2 V square. So we take everything into our considerations, samakan dia, tolakkan dia. So that is our value, the non-conservative value, until we can get, the value of V that is equivalent to 1.3 meter per second. That is the one thing that you can do. You can always refer to these examples. It's very good examples to understand the concepts of non-conservative force. If we do a conservative force, then we can simply say a total mechanical energy, which is EI equals to EF. But when we do a non-conservative force, we need to calculate separately. What is EF? What is EI? And the non-conservative work is EF minus EI. Dan daripada situlah nanti kita boleh dapatkan value dia lagi. Okay, so calculate the non-conservative work. Recall that the force friction Fk equals to mu Kn, and it points the opposites to the displacement. Okay. Okay. Right. So let's go to the power. Let's go to the power. So what is power? Power is a measure of the rate at which work is done. At which work is done, that means power is equivalent to work over time. Okay, work over time, in which they will give you unit of joule per seconds. Joule per seconds, or we can call that as watt. Okay, so one horsepower is equivalent to, this is how we're gonna relate between watt and horsepower. So 746 watt is equivalent to 1 horsepower. Okay, so let's look at the examples. Right. To pass a slow-moving truck, you want your fancy 1,300 kilogram car to accelerate from 13.4 meter per second, which 13.4 meter per second, which is at 30 miles per hour, to 17.9 meter per second, or which 40 miles per hour in 3 seconds. What is the minimum power required for this pass? Okay, so in order to do that, we need to calculate the work, okay, by the use of work and also velocity here, or speed. So W is equivalent to delta KE. So right now we have half mv final square minus half mv initial square. Okay, half mv final square, half mv initial square. So you just use this value to get delta K. Delta K is the work. So we need to use that delta K, divide with time to get the 3.405 10 power 4 watt. Just leave it there, or you want to convert it into horsepower. Then you can divide it with the 746 watt to get the horsepower. Okay. All right. If an object is moving at a constant speed in the face of friction, gravity, air resistance, and so forth, the power exerted by the driving force can be written as what? Okay. So normally the power driven by these kind of things, especially when the use of force. Okay, we know work over time. So what happens is we try to define work in terms of force and displacement. So F d over time. So in this case, we take d over t. Okay, remember what is the displacement over time? Is also equivalent to Fv. Okay, the power can be written down in terms of force times velocity. Okay, force multiplied with the velocity. So we can also get watts. Okay, how many watts? Okay, all right. So let's look at the examples again and again. A lot of examples in this case, right? So, 1,000 kilogram elevator carries a maximum loads of 800 kilogram. A constant frictional force of 4,000 Newton retards its motion upward. What minimum power in kilowatts and in horsepower? Okay, in this case, very different because it needs to find the power in terms of kilowatts, and in horsepower. That means you need to answer it in terms of kilowatt and horsepower. Okay, you need to answer it based on what they need. Okay, must the motor deliver to lift the fully loaded elevator car at a constant speed of 3 meter per second. Okay, so in this case, we need to know, okay, this is mg. Okay, we have a T, the tension, and we also have a frictional force, okay, because it's retard about 4,000. So it also contains 4,000 going down. So T minus F minus mg. So we bring everything to the other sides, which means we have mg plus F. So mg is 1,800 times with the gravity 9.8 times with the plus with the 4,000. So you will get 2.16 10 power of 4 Newton as a tension. Okay, so you can say that the tension is part of force. So in order to find work, P equals to Fv. So you can get this tension into the force. Okay, because force and tension is quite the same. So times with the 3 meter per second. So you will get 6.48 times power of 4 watts. But the question needs you to answer it in kilowatt and also horsepower. So you must answer it until you get kilowatt and horsepower, just for the sake of these examples. Okay, but normally we just calculate until watt. The watt is still is the SI unit for power. Okay, this is also another example. Okay, the killer whales are known to reach 32 feet in length and have mass of over 8,000 kilograms. They are also very quick, able to accelerate up to 30 miles per hour in a matter of seconds. So when you traveling have some sort like 32 feet, okay, 30 miles per hour, you need to convert it to the correct SI unit. Okay, for example, this one should be in meter per seconds. This one you need to measure it in length. Okay. Okay, so you just fast forward, so you can get the work done equivalent to 9.6 10 power of 4 watt. Okay, so this one is about speedboat. Okay, I don't want to go details on this part. You can do on your own examples. I just want to focus on the last part of this chapter, which means the potential, energy curve, and equipotentials. Okay, the potential curve and the equipotentials, but specifically, straight go to the variable force. Okay, work done by a variable force. For example, okay, when you be given a diagram or a graph of force against position, so you may see that a constant force, okay, is given by the straight line. Okay, a constant force and the area under the graph is called area. Is called at a certain from one point to another point, so we can get work. Okay, when constant force against position, so the area under the graph, you can get work. Okay, so if the force takes on several successive constant values, so you may see that there will be a difference in terms of work done. Okay, and how about this kind of graph? Okay, where you see that this is the a curve graph. Okay, that means you can do some approximation. Okay, approximation to that value, because we can say that the area under the graph for the curve graph, okay, based on your knowledge in maths, of course. Okay, so you may want to do some integration, a normal integration to this part, because the integration will give you an area, okay, from the graph. Okay, in this case, we want to highlight it that, okay, the work, but the use when you see the graph of force against positions, so from the Hooke's law, you can see that the work done again for the against the force against position is based on half kx squared. Okay, if you have a force needed to stretch a spring, so, okay, so we have F equals to kx, that is the force, and when it involved in the concept of positions, it also the work is also based on half kx squared, which means from the graph of F, force against position, okay, the area under the graph is given by half kx squared. Okay, and then in the end, okay, we want to use the half kx squared when we're dealing with the situation where you've been given a graph of force against position. Okay, force against positions. So you may want to find the area under the graph. Which area? So it depends on the value of the area. Okay, because you can find you can minus. Yeah, for example, in this case, okay, A, B, C, D. Okay, A, B is 0 to 4, while C, D is 4 to 7. Okay, so you need to calculate it separately. Okay, in order to get work done. Okay, so I think that will be the end of our class, the end of this chapter. Okay, because it should be done. Any questions so far? Do you have any questions? Ada soalan tak?